Let's talk about areas and perimeters of triangles and the geometry of circles. We already talked about how the area of a rectangle is length times width, and the area of a parallelogram is the length times the height, where the height is the perpendicular distance between the two opposite sides. Because I could take this triangle right here off, attach it here, and it would therefore become a rectangle whose width was this height and whose length was the same as the length of the original parallelogram. Now, with a triangle, you can take any triangle and make a parallelogram by just flipping it over any of the sides. If I flip this over this side, this way, I would get this parallelogram. I could flip it over another way, over this side, and get this parallelogram. So you can always make a parallelogram out of a triangle. And since the height of, since the area of the parallelogram is going to be the base times the height, and since half of a triangle or half of a parallelogram gives us the triangle, then the area of the triangle is 1/2 the base times the height, where the base is any side, does not matter which side, and the height is the perpendicular distance from the other vertex, the one that's not on the base. So it's the distance from the vertex to the base at right angles, not like to the middle of it. So if I have a triangle like this, the area of this triangle, if I choose this one to be the base, just because it's sitting on it, but it doesn't make any difference, then the distance from the other corner straight to the base would be the height. And the area is going to be 1/2 times the length of the base times the height. Now, another triangle that people work with a lot would be a right triangle. With a right triangle, the area is going to actually be the length of the two legs because these two legs would constitute, if you let one of them be the base, the other one will be the perpendicular distance from the other corner to that. So the area of a right triangle, if we, as usual, refer to the legs as A and B and the hypotenuse as C, it's going to be 1/2 times A times B. Also, keep in mind that the Pythagorean Theorem, which is where we typically get the A, B, and C from, A squared plus B squared equals C squared, gives us the relationship between the lengths of the sides. And of course, the perimeter is always just the sum of the sides. So with a right triangle, the perimeter is A plus B plus C. Don't mix it up with the Pythagorean theorem. It's not unusual to know the lengths of the three sides without knowing the height in between. So I'm going to call these A, B, and C, although this is not intended to be a right triangle. We have Heron's rule, which will let us calculate the area of a triangle when we know the lengths of the three sides, but not the height. Now, using the height is actually much, much easier. Heron's rule is kind of long and involved, but it's not that bad. S in Heron's rule is 1/2 of the sum of the sides, or 1/2 of the perimeter. So it would be 1/2 of A plus B plus C. Now, used in the area formula, where the area of a triangle is S times S minus A times S minus B times S minus C. The area is this value S times the difference between S and each individual side, all multiplied together, and then take the square root of the whole thing. Let's say we had a triangle and the lengths of the sides were 9, 11, and 14. So S is going to equal 1/2 of 9 plus 11 plus 14. That would be 1/2 of, let's see, this is 20, 34. Half of 34 is 17. So the area is going to be 17 times, I'll write it all out, 17 minus 9 times 17 minus 11 times 17 minus 14. So we've got the square root of 17 times, this is going to be 6, no, sorry, 8 times 6 times 3, which is going to be the square root of Time to get out the calculator here. 17 times 8 times 6 times 3. I get 2448. And so that square root is going to be approximately, I get 49.47727, however many decimals they want you to take it out. Let's say they wanted this to just one decimal place. So one decimal place would be the 4. Look at the next one is a 7, so this needs to go up. So 0.5. And because this is area, this is going to be in square units. How would we find the area of the part of this that's in red? There's no formula for that now. There's no formula for how to get the area of a square with a circle in it that's on the outside of the circle and on the inside of the square. But basically, you can probably see that if we were to take the area of the square and subtract the area of the circle, it would leave the red part. So first of all, how do we get the area of a square? Well, the area of the square is going to be length times width, or just one side squared. However, we don't have the side. We have what will turn out to be half of the side. If we drew this all the way through, you can see that we could, if we draw lines through the center of this circle, then we would also have 1/4 of the square in each of these. So one way we could get the area of this square, and there's lots of different ways to do it. One thing would be to say that the area of this smaller square here is going to be 5 times 5, so 25. There's 4 of those. So one of many ways to do it would be to say that it was 4 times 5 times 5. 4 squares that were of area 5 times 5. The area of the circle, since this is actually the radius, is going to be pi times 5 squared. So we've got 4 times 25 is 100 minus 25 pi. And if we approximate pi at 3.14, I reversed the order here, so forgive me for that. This is going to be 100 minus 25 times 3.14. Got 78.5. And that subtracted from 100 is 21.5. So 21.5 square units is the area in red. There's always lots of ways to do. What if instead of a circle in a square, they had given us a square in a circle? And the distance they gave us was the radius, but in this case, instead of half of a side, it's going to be half of the diagonal. So suppose this was 5. So now the difference between the two. Now the circle has the larger area. So it's going to be the area of the circle minus the area of the square this time. The area of the circle is still going to be pi r squared. Area of the square. There are several ways to do this. One way would be to take half of this square as being a right triangle. The hypotenuse now is going to be 10. This is a square. It has to be a square to be inscribed something like a circle. So using the Pythagorean Theorem, and this is again one of several ways we could do this. There's a bunch of them. But we could say that a and b are the same, so we could just actually call this a squared plus a squared equals, if half of this is 5, then the whole thing is 10, so this is going to be 10 squared. 2a squared is 100. A squared, when I divide by 2, is going to be 50. So a is going to be the square root of 50, which is approximately 7.071. So the radius is 5. So we've got 5 squared is 25. This is going to be 25 pi minus, now the area of the square, if one side, well, actually, we didn't even need to do this. The area of the square is going to be a squared. So this is going to be the 50. See, if this distance is the square root of 50, and this distance is the square root of 50. The square root of 50 times the square root of 50 is the square root of 50 squared, which is 50. So a squared is the area. So just 25 minus 50, 25 pi minus 50. 25 times 3.14 is going to be about 78.5 minus 50 is going to be 28.5. Came out pretty close to the other one, didn't it? So on these kind of problems, there's always multiple ways to do them. Lots and lots. The answer is going to be the same regardless, but the way you do it and the way your buddy does it might be different. That doesn't necessarily matter.